Right now, in every direction you can look in the night sky, 250 billion stars are spinning in our galaxy alone. And as far as we can tell, after 70 years of careful listening, every one of them is silent. There is no signal, no call, no reply. Every system we have surveyed, every star we have catalogued, every planet we have characterized has returned the same null result. The radio bands carry only the hiss of cold cosmic background, the chatter of pulsars, the quiet thermal glow of galactic dust. The optical sky shows us starlight, planet transits, the slow brightenings and dimmings of variable stars. There is, in the data we have collected, nothing that has been confirmed as a message from anyone else. The galaxy is older than the Earth. The galaxy is 105,000 light years across. The galaxy contains, by best current estimates, between 11 and 40 billion rocky worlds in the temperate zones of their host stars. By the simple arithmetic of probability, intelligence should have emerged many times. Civilizations should have arisen. Some of them should have built radios. Some of them should have built probes. The probes should have reached us by now. They have not. Tonight we are going to walk through what this might mean. You do not need to hold every number. Some you will. That is enough. The silence is long. It has been here for as long as we have been listening, and it was here for a great deal longer before we knew how to listen. We have a couple of hours. If you have come here to rest, let this carry you. The silence we are about to walk through is not threatening. It is at most the silence of a long evening, in a quiet room, on a planet where you happen to be. Now, let us pull back. Let us begin not with the cosmos, but with a man at lunch. The year is 1950. The place is Los Alamos, New Mexico. The lunch is being taken in the cafeteria of the laboratory that had, 5 years earlier, designed the first atomic weapons used in war. The conversation that day is informal. The participants include Edward Teller, Emil Konopinski, Herbert York, and Enrico Fermi. They are discussing, among other things, recent newspaper reports of unidentified flying objects. The conversation drifts. The other participants make jokes about flying saucers. Fermi, who has been quiet for some time, suddenly turns to the others and asks in his characteristically blunt manner where everybody is. The question, in its full form, was this: given the age of the galaxy, which is at least 10 billion years, given the number of stars in the galaxy, which is somewhere in the hundreds of billions, given that the laws of physics are, presumably, the same everywhere, and that life, presumably, can arise on any world where the conditions are right, given that interstellar travel, even at modest fractions of the speed of light, would allow a civilization to colonize the entire galaxy in approximately 10 million years, then, by the simple arithmetic of all of this, the galaxy should have been colonized many times over. Where, then, was everybody? Fermi's question, posed at a lunch table over what was probably an indifferent meal, would become, in the decades that followed, one of the central questions of modern astronomy. It would be formalized, it would be studied, it would be the subject of papers, books, conferences, and survey campaigns. The question has not yet been answered. The question, in academic literature, is called the Fermi Paradox. Tonight we are going to walk through it slowly. I want to be careful about how we approach this. The Fermi Paradox is not, despite its name, a paradox in the strict mathematical sense. It is an observation, combined with a set of expectations. The observation is that we have, despite many decades of careful searching, found no evidence of extraterrestrial intelligence. The expectations are based on assumptions about how often life arises, how often life becomes intelligent, how often intelligent life develops technology, and how often technological civilizations make their presence detectable. The mismatch between the observation and the expectations is what makes the question interesting. Something is, somewhere in the chain of expectations, wrong. The question is what? There are broadly 3 classes of possible answers. The first class says that the expectations are wrong. Life is not as common as we think. Intelligence is rarer than we think. Technology is harder than we think. The galaxy is not in fact full of civilizations, and the silence we observe is exactly what we should expect. The second class says that something prevents civilizations from being detected. Either they choose not to broadcast, or they have learned, through experience, that broadcasting is dangerous. or they have evolved beyond the use of the kinds of signals we are looking for. The civilizations exist, but they are silent. The third class says that civilizations exist for a time, but they do not last. Something interferes with the long-term survival of technological societies. The lifetimes are short. The probability of two civilizations existing simultaneously, in detectable range of each other, is correspondingly low. The galaxy may be full of ruins, but few living transmitters. Each of these classes has its own internal logic. Each has its own set of evidence and counter-evidence. Each implies something different about our own situation. Tonight we are going to walk through the most uncomfortable version of the third class, the version that says that civilizations do not just fade quietly, they are extinguished. That version is called, in the literature, the dark forest hypothesis. Now let us pull back. Before we walk through the hypothesis, I want to spend a little time on the evidence we have for the basic observation. The observation is that the sky is silent. The observation, like all observations, has limits. We have not searched everywhere. We have not listened for everything. There are entire classes of signals we may not be capable of recognizing. Before we walk through that, let me hold what the observation actually consists of, because the silence, as a piece of data, has been carefully built up over the course of decades of work. It is not a casual statement. It is the cumulative result of every serious effort that has been made to listen. The history of listening, in its formal scientific form, begins in 1959. That year, two physicists at Cornell University, Giuseppe Cocconi and Philip Morrison, published a short paper in the journal Nature. The paper was titled Searching for Interstellar Communications. It argued that if any extraterrestrial civilizations existed, the most likely channel for them to broadcast on would be the radio band. Radio waves penetrate dust and gas. Radio waves can be made narrowband, which means they can be distinguished from natural sources, which are typically broadband. Radio technology is, the authors argued, a natural early development for any species that achieves industrial sophistication. Therefore, the radio sky was where to look. The paper concluded with a famous line: the probability of success in such a search was, the authors wrote, difficult to estimate. But if a search were never undertaken, the chance of success was zero. The argument was a prompt. The community responded. The first systematic search for extraterrestrial radio signals was conducted in 1960 at the Green Bank Telescope in West Virginia by Frank Drake. The search was called Project Ozma, after the Queen of the Imaginary Country in The Wizard of Oz. The choice of name reflected a certain wry self-awareness on Drake's part. He knew he was looking for a fairy tale. The project surveyed two nearby stars, Tau Ceti and Epsilon Eridani, for several hundred hours over the course of a few months. The instrument was an 85-foot radio dish, the largest available at the time. The frequency range was narrow, focused around the 21-centimeter hydrogen line, which Drake and others had identified as a natural communication channel for any civilization that knew radio physics. The search returned no detected signal. That was the first formal attempt. Many followed. Over the subsequent decades, surveys grew in scope. Larger dishes, wider frequency ranges, longer integration times, more stars. The Arecibo dish in Puerto Rico before its collapse in 2020 conducted long campaigns of radio observation. The Allen Telescope Array, built in California specifically for SETI work, came online in 2007. The FAST telescope in southern China joined the effort in 2016. Most recently, the Breakthrough Listen initiative, funded with $100 million by the Israeli-Russian investor Yuri Milner, has been conducting the most systematic and sensitive survey ever performed. The cumulative search, summed across all these efforts, has covered a small fraction of the relevant parameter space. The relevant parameter space includes every frequency at which a civilization might choose to broadcast, every direction in the sky, every moment in time. The fraction we have searched, by standard estimates, is on the order of 1 part in a quintillion. That is small. If we have searched 1 part in a quintillion of the possible signal space, and we have found nothing, the result is consistent with two possibilities. The first is that there are no signals to find. The second is that the signals are there, but we have not yet looked in the right place, at the right time on the right frequency. We do not yet know which possibility is correct. The natural reading from a Bayesian standpoint is that the silence is suggestive but not conclusive. We have insufficient data to distinguish between the hypotheses. We need to keep looking, but the silence, even partial and inconclusive, raises the question: why have we not found anything in the part of the space we have searched? The search has been substantial. The instruments have been sensitive. If signals were common, we should, statistically, have caught at least a few. We have caught nothing that has been confirmed. There have been hints. The WOW signal in 1977 from the Big Ear Telescope in Ohio, a 72-second narrowband emission that fit the predictions for an artificial signal. It was never repeated. The source has never been identified. The signal remains unexplained. There have been other transients. In 2020, the Breakthrough Listen team flagged a candidate signal from the direction of Proxima Centauri, designated BLC-1. After careful analysis, the signal was ruled out as terrestrial interference. It was not, in the end, a signal from elsewhere. There have been, over the decades, dozens of similar candidates. Each has been investigated. Each has eventually been explained as a natural phenomenon, a terrestrial source, or a problem with the equipment. No signal has to date survived the scrutiny. Let me sit with the WOW signal for a moment, because it is the most famous of the candidate detections. On the night of August 15th, 1977, a volunteer astronomer named Jerry Ehman was reviewing printouts from the Big Ear Radio Telescope, located at the Ohio State University Radio Observatory in Delaware County, Ohio. The telescope had been operating for several years as part of a long-running survey for extraterrestrial signals. Each night, the telescope's drift scan technique recorded what passed through its beam as the Earth rotated. The data came out as a printout of letters and numbers, with each entry representing the intensity of the signal in a particular frequency channel during a particular brief time interval. Most of the printouts were quiet. The numbers were low. The letters representing the intensity on the scale used by the Big Ear team were typically blanks or low single digits. On that particular night, in a particular frequency channel near the hydrogen line, the intensity rose for 72 seconds, peaked at a level high enough to merit the highest letters on the chart, and then faded back. The shape of the signal, plotted against time, was exactly what would be expected for a narrowband source passing through the telescope's beam as the Earth rotated. Ehman, reviewing the printout some days later, recognized that this was exactly what they had been looking for. He circled the entry with a red pen and wrote, in the margin, the single word, WOW. The signal has since then been called the WOW signal. The signal has never repeated. Every subsequent attempt to detect a similar signal from the same direction, with comparable instruments, has returned a null result. Various natural explanations have been proposed, including the possibility that the signal was a reflection from a piece of space debris, or that it came from a comet whose hydrogen cloud crossed the telescope's beam. None of these explanations has been definitively confirmed. The signal sits today in the unresolved category. It is the closest thing we have to a confirmed candidate. It is not, by current standards, a confirmed detection, but it is also not explained. Most working researchers in the field treat the WOW signal as an unexplained anomaly that is most likely natural in origin, but that has not been definitively assigned to any particular natural source. The signal is, in some sense, the iconic example of the kind of candidate that the search produces. Promising, unrepeated, inconclusive. The cumulative result is that we have searched, found nothing, but searched only a small fraction of the possible space. That is the observation. Now let us walk through what the observation might mean. The first class of explanation, as I mentioned, is that the expectations are wrong. Life is rarer than we think. Intelligence is rarer. Technology is harder. This explanation is consistent with the data, but it requires that several of the steps in the development of intelligent life be much harder than they appear on Earth. Life on our planet emerged relatively quickly after the conditions allowed. The first single cells appear in the fossil record within perhaps 500 million years of the formation of stable oceans. Complex life took longer, perhaps 2 billion years, to make the prokaryote to eukaryote transition, but it did eventually occur. Intelligence emerged still later in the last few million years. Technology arose in the last 10,000. Radio capability is 70 years old. The Earth's timeline suggests that, given a habitable world, The steps toward intelligence may not be especially rare, but we have only one data point. The single data point is consistent with many different probabilities for each step. In 2018, a group of researchers at Oxford published a paper titled Dissolving the Fermi Paradox. They argued that the standard probabilities used in the Drake equation, which estimates the number of communicating civilizations in our galaxy, have been treated with insufficient skepticism about the uncertainties. When the uncertainties are propagated correctly, using the most defensible priors, the median estimate for the number of civilizations in our galaxy drops to less than 1. The Fermi paradox, in this view, dissolves. We are alone, or nearly alone, and that is exactly what we should expect. This argument is not in itself conclusive. The priors used in the calculation are themselves uncertain. The exercise is, in some sense, garbage in, garbage out. But it makes a useful point. The expectation that the galaxy is full of civilizations is not a robust prediction of any physical theory. It is a guess based on extrapolating from one data point. If the extrapolation is wrong, the silence makes sense. This is the comforting version of the answer. We are alone. The reason we have not found anyone is that there is no one to find. The galaxy is biological in only one place, namely the small wet world we inhabit. I want to walk through this for a moment, because it is, in some sense, the most likely answer. If life is rare and intelligence is rarer, then our presence in the galaxy is an exceptional event. Not impossible, but exceptional. The galaxy got lucky. The galaxy may have got lucky in a few other places as well, but the others are too far apart for any of them to be in detectable range of any other. We sit, in this picture, in a particular small bubble of life, with no contemporaries within reach. This is a humbling picture. It is also in some sense peaceful. We are not, in this picture, a small frightened civilization in a galaxy full of others who might be hostile. We are simply alone. The silence is the silence of an empty room. Most working scientists who have thought carefully about the question, when pressed, lean towards some version of this answer. The simplest explanation for the silence is that there is nothing making sound. The simplest explanation is that we are alone, or that the others are too rare and too far to matter. Let me bring that closer. If we are alone in our galaxy, the consequences for our own future are profound. We are responsible in some sense for what intelligence does in this region of the universe. We are the only ones to make the choices. We are the only ones to record. We are the only ones to remember. This is a large responsibility. It is also, in another sense, a quiet kind of freedom. The galaxy is ours to inherit, if we wish to. The other star systems are empty. No one is competing for them. No one is preparing to defend them. The galaxy is open. That is one picture. It is, I want to emphasize, an entirely plausible one. The data is consistent with it. But it is not the only possibility. Now let us pull back, fellow night watcher, and walk through the second class of explanation. The second class says that civilizations exist, but they remain silent. The galaxy may be full of intelligence. The intelligences may simply be choosing not to broadcast. There are several variants of this explanation. The first variant is what I will call the indifference variant. The civilizations exist, they are old, they have moved past the use of the kinds of signals we look for. They communicate with each other, perhaps by means we cannot detect. They have no interest in advertising their presence to a young world like ours. They are, in some sense, beyond us. This variant is consistent with the data. It is, however, anthropomorphic. It assumes that civilizations make choices that resemble human choices, with motivations that resemble human motivations. There is no particular reason this assumption should be correct. The second variant is what I will call the prudence variant. The civilizations exist, they are aware of the universe, and they have decided, for reasons of survival, not to broadcast. They have perhaps encountered evidence that broadcasting is dangerous. They have perhaps learned, through experience or through theoretical analysis, that revealing one's location to the cosmos is a poor strategic choice. This is where the dark forest hypothesis lives. Let me walk through the argument slowly. The argument begins from 3 assumptions. The first assumption is that survival is the primary goal of any sufficiently advanced civilization. The second assumption is that civilizations cannot reliably assess the intent of other civilizations. The third assumption is that at sufficient technological development, Civilizations are capable of weapons that travel at significant fractions of light speed. The weapons may be relativistic kinetic impactors, may be coherent gamma-ray pulses, may be self-replicating attack swarms, may be other things we cannot yet imagine. The exact mechanism is not the point. The point is that, at sufficient development, a civilization can effectively eliminate another from across interstellar distances, without warning, at relatively low cost. Given these three assumptions, the argument proceeds as follows. Consider a civilization that has just acquired the technology to detect and communicate across interstellar distances. The civilization has a choice. It can broadcast its presence, sending signals into the galaxy that announce its location and its level of development. Or it can remain silent. If it broadcasts, the signal cannot be retracted. The signal travels indefinitely, at the speed of light, in all directions. Any civilization in the galaxy that is listening can pick up the signal and learn the broadcaster's location. If the listening civilization is friendly, nothing bad happens. Perhaps a return signal is sent. Communication begins. The galaxy becomes a community. AI. If the listening civilization is hostile or simply indifferent to the broadcaster's survival, then the broadcaster has provided its coordinates. A weapon can be dispatched. The weapon, if it travels at relativistic speeds, may arrive without warning. The broadcaster has, by signaling, made itself vulnerable. The asymmetry is crucial. A civilization that signals risks everything, in the event of a hostile listener. A civilization that does not signal loses very little. It cannot communicate. But it does not become a target. If the civilization is rational, and if its primary goal is survival, then the rational choice is to remain silent. The expected payoff of broadcasting is negative, because the worst-case outcome, annihilation, is far worse than the best-case outcome, communication with a friendly neighbour. This is the dark forest argument. The argument was articulated in detail, in fictional form, by the Chinese science fiction author Cixin Liu in his novel The Dark Forest, published in 2008. Liu did not invent the underlying logic. The logic had been developing in various forms in the SETI community for decades. Liu's contribution was to give the argument a vivid frame. The galaxy, in his telling, is a dark forest. Every civilization is a hunter, moving silently through the trees. Each hunter is afraid. Each hunter knows that other hunters exist. None of them can afford to make a sound. The moment a hunter speaks, the moment a hunter reveals its location, the other hunters fire. In the dark forest, the only safe strategy is silence. The implication, if the argument holds, is that the galaxy is full of intelligence, but that the intelligence is all hiding. The silence we observe is not the silence of an empty room. It is the silence of a room full of careful, frightened residents who have agreed, by tacit consensus, not to make any noise. Stay with me here. I want to be careful about this argument. It is, I emphasize, a hypothesis. It is not established. It rests on assumptions that may not hold for all civilizations. It is a theoretical possibility, not an observation. The assumptions can be questioned. Perhaps survival is not the primary goal of all civilizations. Perhaps some civilizations are willing to take the risk of broadcasting in pursuit of communication. Perhaps the technology of relativistic weapons is not actually achievable, or is not actually as cheap as the argument requires. Perhaps the game theoretic analysis is wrong, and there exists a cooperative equilibrium that we have not yet identified. All of these are possible objections. None of them is, by itself, decisive. The argument's force, in the end, is that it is consistent with the observation. If the galaxy were full of careful, silent civilizations, the sky would look exactly the way it looks. Empty. This is one of the things that makes the hypothesis uncomfortable. It is consistent. It explains the delta, it cannot be ruled out, B-E-hover-R, and it implies, if it is correct, that we are in serious trouble. Now let us hold that for a moment. Let me sit with the game theory of this for a moment, because the argument is, in some sense, a rigorous one. Consider two civilizations. We will call them A and B. Each is technologically capable of interstellar communication. Each is also technologically capable of producing a weapon that can travel at relativistic speeds and destroy the other. Each civilization has, in this scenario, 4 possible strategies. Civilization A can choose to either broadcast or stay silent. Civilization A can choose to either attack or not attack if it detects Civilization B. The strategies form a game. The payoff matrix in the simplest version of the game has 4 cells. If both civilizations broadcast and neither attacks, both gain the benefit of communication. If both broadcast and both attack, both lose. If A broadcasts and B does not, then B has detected A, but A has not detected B. B can choose to attack A from safety. A has no defense. The payoffs, when worked through, suggest that the dominant strategy, in the absence of any way to assess the other civilization's intent, is to stay silent, and, if a signal is detected, to attack. This is, I want to stress, the result of a specific set of assumptions. The assumptions are that survival is paramount, that intent cannot be assessed, and that weapons of the required class are available. Each of these assumptions can be questioned, but the assumptions as stated are not unreasonable, as they reflect a hard-headed reading of what a civilization concerned with its own survival might do, in the absence of any way to verify the intentions of other civilizations. If the game is played repeatedly across the galaxy by many civilizations over many millions of years, the equilibrium that emerges is silence. Civilizations learn, by selection pressure, if not by reasoning, that the optimal strategy is to remain quiet. The ones that broadcast are eliminated, the ones that remain silent persist. The galaxy that we observe in this picture is the galaxy of the survivors. They are silent because silence is what survives. We have been broadcasting, in various forms, for over 100 years. Radio, television, radar. The leakage from these systems travels into space at the speed of light, in roughly omnidirectional patterns. Our signals have, in principle, reached every star system within a 100 light-year radius of Earth. That includes a substantial number of stars, hundreds, perhaps thousands. Many of them have planets. If the dark forest hypothesis is correct, and if any of the recipients of our signals have hostile intent, then a response in some form may already be in transit. This is the part of the argument that the literature treats most seriously. The argument, applied to us, says that we have already made a strategic error. We have already revealed our location. The harm, if there is to be harm, is already on its way. There's nothing we can do about this. The signals have left. They cannot be recalled. The only remaining variable is what the recipients, if there are any, choose to do. Let me bring that closer. The argument suggests that we should, at minimum, stop broadcasting deliberately. Programs like the Arecibo message of 1974, which sent a deliberate transmission toward the globular cluster M13, are, by the lights of the dark forest argument, dangerous. They reveal our location to anyone within range. The argument has, in fact, prompted serious debate in the SETI community about the wisdom of active broadcasting. The community has, by consensus, moved away from active broadcasting in recent decades. The current convention is to listen, not to transmit, to detect, not to announce. Whether this caution is warranted is, again, an open question. The argument may be correct. It may be wrong. We do not have the data to settle the matter. What we have is the silence. And the silence by itself is consistent with the argument. Let me sit with one more aspect of the dark forest argument, because it has a particular geometry that is worth holding. The argument depends in part on the idea that the universe contains many civilizations. If there are few, the equilibrium may not establish itself. If there are many, the selection pressure for silence becomes strong over time. Civilizations that broadcast are eliminated. Civilizations that remain silent persist. The argument also depends on the idea that over cosmic time, the cumulative effect of many encounters between civilizations produces a stable strategy. The strategy is silence. The stable equilibrium, after enough time and enough encounters, is universal silence. This kind of argument is familiar in evolutionary biology. The stable strategies are not chosen by individuals. They are selected by the cumulative effect of many interactions over many generations. The strategies that survive are the ones that, on balance, lead to persistence. The strategies that do not survive are the ones that, on balance, lead to elimination. Silence in the dark forest picture is the strategy that survives. Broadcasting is the strategy that does not. This is a chilling reading. It implies that the silence we observe is, in some sense, the result of a long history of broadcasters being eliminated. We, in our small recent broadcasting, are repeating a pattern that, by this argument, has many times before led to extinction. It also implies that even if the argument is wrong in its details, the equilibrium pressures may favour silence. There may be other game-theoretic reasons, less stark than the dark forest, that also push civilizations towards silence. The universe may, in this picture, be silent for game-theoretic reasons, even if the dark forest specifically is not the right description. We do not know. We cannot at present know. What we have is the silence, and the question of what the silence might mean. Stay with me here. Let me also walk through what the literature calls the percolation model. This is a different way of thinking about the silence, due to Geoffrey Landis and others in the 1990s. The percolation model says the following. Suppose that civilizations, when they arise, sometimes choose to expand into space, and sometimes do not. The choice is, in some sense, random. Some civilizations colonize, some do not. Whether a civilization colonizes depends on its particular culture, its particular technology, its particular circumstances. If the fraction of civilizations that choose to colonize is below a certain threshold, the colonization wave does not propagate. Civilizations may exist throughout the galaxy, but the wave of expansion does not, by random chance, reach us. The colonizers do not, in this picture, ever extend their reach far enough to make contact with all of the habitable systems in the galaxy. If the fraction is above the threshold, the wave propagates. Civilizations cover the galaxy. Every habitable system is visited. The threshold in standard percolation calculations is around 25%. Below 25% of civilizations choosing to colonize, the wave does not propagate. Above, it does. This is a curious result. It suggests that the silence may be the result of a subcritical percolation. Civilizations exist. They do not all colonize. The ones that do not extend far enough to cover everything. We sit in this picture, in a part of the galaxy that the colonizers have not, by random chance, reached. The picture is consistent with the data. It is also testable in principle. As our surveys grow more thorough, we should be able to constrain the fraction of habitable systems that show signs of colonization. So far, the constraint is loose. The fraction could be 0, the fraction could be small. We do not yet have the resolution to say. Now, let us pull back, and let us walk through the third class of explanation. The third class says that civilizations exist for a time, but they do not last. The lifetimes are short. The probability of overlap is low. The galaxy is full of ruins but few living transmitters. This explanation involves what Robin Hanson, in 1998, called the Great Filter. The Great Filter argument is, in outline, simple. There exists at least one step in the development of intelligent technological life that is extremely improbable. The step might be early, in the emergence of life itself. The step might be middle, in the development of complex multicellular forms, or in the emergence of intelligence. The step might be late, in the survival of technological civilizations beyond a certain threshold. If the step is early, behind us in our own history, then we have already passed it. The path forward is, in principle, clear. We may yet survive and thrive. If the step is late, ahead of us in our own history, then we have not yet passed it. The path forward is, in principle, dangerous. We may not survive. The argument is, in essence, a probabilistic one. Given the absence of observable civilizations and given the apparent ease with which life arose on Earth, we must conclude that something is extremely unlikely in the chain of events from molecular chemistry to detectable civilization. Whatever that something is, it constitutes the filter. Hanson's chilling observation is that we do not know where the filter is. If it is behind us, we are lucky. We have already made the improbable transition. The galaxy is empty because everywhere else, the same improbable transition failed to occur. We are the exception. If it is ahead of us, we are unlucky. The transition lies in our future, and the typical outcome is failure. Other civilizations have arisen, briefly, and then collapsed. The remains are scattered across the galaxy. They are not in transmitting state. They are not detectable. They are gone. The location of the filter is, by far, the most consequential thing we can know about our future. There are several possible candidates for the filter, each of which would, if confirmed as the cause, change our outlook profoundly. Candidates in the past include the origin of life from non-living chemistry. We do not know how this happened. It may be that the chemistry of life, given Earth-like conditions, is essentially inevitable. Or it may be that the specific configuration of chemistry that produced life on Earth was a once-in-a-galaxy accident. We do not have enough data to choose between these. The transition from prokaryotes to eukaryotes is another candidate. This transition, which took place on Earth approximately 2 billion years ago, may have involved a series of fortuitous symbiotic events. Without those events, the development of complex cells, and ultimately of complex multicellular life, would not have occurred. The transition may be rare. Multicellular life itself is a third candidate. The transition from single cells to multicellular organisms has occurred independently on Earth several times. So it may not be a major obstacle, or it may, in some narrower form involving particular kinds of cellular cooperation, be rare elsewhere. The emergence of intelligence is a fourth candidate. Earth has many species. Only one has developed technological civilization. Whether intelligence of our kind is rare or whether it is common but rarely produces civilization is unclear. Candidates in the future include nuclear self-destruction. We have, since 1945, possessed weapons capable of destroying our own civilization. We have not yet used them in that way. Whether we will continue to refrain indefinitely is unclear. Ecological collapse is another future candidate. Civilizations may, by their own activities, destabilize the planetary systems on which they depend. The destabilization may be terminal. Runaway artificial intelligence is a third future candidate, more recent in the literature. A civilization that creates an artificial superintelligence may, if the alignment problem is not solved, be replaced by its own creation. The creation may not preserve the civilization that produced it. Contact with hostile civilizations is a fourth future candidate. This brings us back to the dark forest hypothesis. If the galaxy contains hostile actors, and if we have broadcast our location, then contact is one of the future filters. The list is incomplete. The filter, whichever step it turns out to be, is one of these or something we have not yet imagined. We do not know which. Let me hold this carefully. The filter argument is, in some sense, a Bayesian one. It says that given the observed silence, we can update our probabilities about each of the candidate steps. The steps that were more probable in our prior estimates become less probable in our posterior. The steps that were less probable become more so because the silence is more consistent with there being the filter. Concretely, this means the following. Before the Fermi Paradox is taken seriously, we might have assigned roughly equal probabilities to each candidate filter. After the paradox is taken seriously, we should redistribute the probabilities. The candidates most consistent with the silence are most likely to be the actual filter. The candidates most consistent with the silence are the ones that prevent civilizations from being detectable. Those are, primarily, the late candidates, the ones ahead of us, because civilizations that fail early do not produce visible signs of failure on cosmic scales. Civilizations that fail late after acquiring technology leave traces that we should, in principle, be able to detect. If we do not detect such traces, it is either because there were no civilizations, or because the civilizations failed in ways that left no visible trace. The most worrying possibility, in this Bayesian framework, is the one where the filter lies ahead of us, in a region of capability we have already acquired but have not yet fully tested. Nuclear weapons, artificial general intelligence, ecological systems pushed past their tolerance. Each of these is a potential filter. We have, in some sense, already crossed into the danger zone for each of them. We do not know how dangerous each is in the long run. We have not yet been tested across the millennial scales that the filter argument considers. Our 70 years with nuclear weapons may be a brief, lucky stretch. Our brief experience with artificial intelligence may be a tiny window before something larger comes, or these may be tractable. We may in some sense be able to manage them. The next 1,000 years may be smooth. The next 1,000,000 years may see us settle into a stable technological civilization that lasts indefinitely. We do not know. The filter argument does not by itself tell us which way the dice are weighted. It only tells us that the dice are being rolled and that the silence we observe is consistent with most of the rolls coming up bad. Stay with me here. This is the part of the analysis that is hardest to hold. The filter, if it is ahead of us, implies that our civilization has, with high probability, only a limited time to last. The exact time is unknown. But the typical outcome in the picture is that civilizations like ours do not survive past some threshold. Hold this. If we look back through the history of our species, we see a particular pattern. For most of human existence, our population was small and our technology was limited. We were one species among many on the planet. Our influence on the planet was minor. In the last 10,000 years, agriculture emerged, population grew, cities appeared. The pattern of human influence accelerated. In the last few hundred years, industrial technology emerged, population grew further. The pattern of human influence began to register on the planetary scale. In the last 100 years, nuclear technology, biotechnology, and information technology emerged. The pattern of human influence is now global. Our ability to alter the planet, deliberately or accidentally, exceeds anything in our prior history. This acceleration is recent. It is also, in cosmological terms, very brief. We have been a technological civilization for perhaps 70 years, depending on how you count. Most of cosmic history happened without any technological civilization on Earth at all. The question is whether the next 70 years, the next 700, the next 7,000, the next 70,000 will see us continue, or whether some filter will, in some form, end our particular run. This is the question the great filter argument poses. It is uncomfortable. It is also, in some sense, useful. It clarifies the stakes. It identifies the things that may matter most for our long-term future. Now let me bring this closer. The combination of the dark forest hypothesis and the great filter is, in many ways, the most pessimistic reading of the Fermi Paradox. The combination says that civilizations exist, but that they do not last, and that the reason they do not last is, in part, that they detect and destroy each other. The galaxy is full of intelligence. The intelligence is mostly dead. The intelligence that remains is hiding. This is the version of the answer that nobody wants to be true. It is consistent with the data. It cannot be ruled out. It is also not the only version. The other versions, the comforting ones, the ones that say we are alone or rare or simply not yet found, are also consistent with the data. They also cannot be ruled out. We do not yet know which is correct. We will not know in all likelihood for a long time. What we have is the silence. The silence is what we are walking through tonight. Let me sit with the silence for a moment. The silence is not, in itself, frightening. The silence is what a quiet field sounds like at night. The silence is what a remote sea sounds like on a windless evening. The silence is what an empty room sounds like when the lamps are off. The silence is ordinary in many contexts. It is only when we ask why the silence is there that the question becomes uncomfortable. In a forest at night, silence may mean that the animals are sleeping. Silence may mean that the animals are watchful, frightened of a predator. Silence may mean that the animals are absent. In the galaxy at night, silence may mean that the civilizations are sleeping. Silence may mean that the civilizations are watchful, frightened of one another. Silence may mean that the civilizations are absent. We do not know which. What we have is the silence. Now let me sit briefly with the question of what makes the dark forest hypothesis particularly difficult to dismiss. The argument is, in some ways, robust to many of the obvious counter-arguments. Consider, for instance, the counter-argument that civilizations might communicate by some means other than broadcasting. Perhaps they send probes. Perhaps they encode messages in starlight, in subtle ways we cannot detect. Perhaps they use channels we cannot read. The dark forest argument does not require that all communication be by broadcasting. It only requires that the kinds of broadcasts we make, the ordinary radio and optical signals, are detectable to a sufficiently advanced civilization, and that such broadcasts can be acted upon. The argument does not depend on the specific medium of detection. It depends only on the cost-benefit asymmetry of revealing one's location. Consider, for another, the counter-argument that civilizations might form alliances. Some civilizations might trust each other. Some might cooperate. A community of cooperating civilizations might broadcast to each other freely. The dark forest argument does not exclude this. The argument says that, in the absence of pre-established trust, broadcasting is dangerous. It does not say that all civilizations are hostile. It says that, without a way to verify intentions, the rational strategy is silence. If two civilizations have already established communication, perhaps through a previous careful exchange, they might continue to broadcast to each other. But the first broadcast, the one that announces a civilization's existence to the cosmos at large, is, in this picture, the dangerous one. The argument also accommodates the possibility that some civilizations are willing to take the risk. Perhaps some civilizations have a different value system. Perhaps some civilizations believe, for reasons of their own, that broadcasting is worthwhile. Such civilizations would, in this picture, eventually be eliminated by the careful ones, but while they exist, they would, in principle, be detectable. The fact that we have not detected any may mean that no such civilizations exist within our reach, or that the elimination process is fast enough to keep the population small, or that they exist but at distances too great for us to catch. This is the structure of the argument. It is again internally consistent. It is again consistent with the data. It cannot be ruled out. What we have in the end is a hypothesis that the silence is not absence. The silence is, in this picture, deliberate. The silence is what the survivors do. Hold this. If the silence is deliberate, then there are, in this galaxy, residents we will not meet by passive listening. Our instruments will not pick them up. They have made sure of that. They have, by their choice of strategy, made themselves invisible to us. If the silence is absence, then there are, in this galaxy, only the empty spaces between unpopulated stars. We are alone. Our listening, even if extended indefinitely, will hear nothing. Either way, what we hear is silence. Either way, the data by itself does not distinguish. We continue. Stay with me here. I want to walk through a few more of the candidate explanations for the silence, because the dark forest and the great filter are not the only options. The fourth class of explanation says that civilizations exist, but that they are too distant from us in time or space to be in contact. The galaxy is large. The lifetimes of civilizations, even if they are not destroyed by filters, may be short compared to the timescales of galactic exploration. Two civilizations may exist within the same galaxy, but separated by such vast distances that no contact is possible within either's lifetime. This is, in some sense, a softer version of the filter argument. It does not require that civilizations destroy themselves. It only requires that they not last long enough to fully colonize. This explanation is consistent with the data. It is also relatively comforting. It suggests that we are not in danger from other civilizations, because we cannot reach them and they cannot reach us. The silence is the silence of vast distance, not of vast extinction. The fifth class of explanation says that civilizations exist, but that they are using forms of communication that we cannot detect. They may communicate by neutrinos, by gravitational waves, by quantum entanglement, by means we have not yet imagined. The radio sky is silent because the radio sky is not where they are talking. This is also consistent with the data. It is also speculative. We have no positive evidence that such communication is possible at interstellar distances, but we cannot rule it out. The sixth class of explanation, perhaps the most exotic, is what is sometimes called the zoo hypothesis. The galaxy is, in this picture, full of civilizations. The civilizations have noticed us. They have decided, for reasons of their own, to leave us alone. They have, in effect, declared the Earth a wildlife preserve. They watch us. They do not interfere. They do not signal. This is consistent with the data. It is, however, anthropomorphic in the extreme. It requires that the civilizations of the galaxy, all of them, have agreed on a non-intervention policy. Whether such an agreement is plausible across vast distances and vast cultural differences is unclear. Each of these explanations has its own internal logic. Each has its own implications. None of them by itself settles the question. What we have is the silence. Let me walk through one more candidate explanation, because it is, in some ways, the most peculiar and the most thought-provoking. The seventh candidate is what is sometimes called the simulation hypothesis. The idea is that we are not, in some sense, in a base-level physical reality. We are instead in a simulation run by some advanced civilization, or by some descendants of ourselves, or by some other unknown entity. The simulation does not perhaps contain other civilizations, because the simulators have not bothered to include them. The silence is the silence of an empty stage, set up for our own particular drama. This hypothesis is, I want to emphasize, untestable in any strict sense. It is unfalsifiable. It is, in some sense, a philosophical exercise rather than a scientific one. But it is, in another sense, internally consistent. It would explain the silence. It would explain a great deal else. The hypothesis has, in recent decades, been advanced by various thinkers, most notably by the Oxford philosopher Nick Bostrom in a paper from 2003. Bostrom argued that, given certain assumptions about the development of computational technology by post-human civilizations, it is statistically more likely that we are in a simulation than that we are not. The argument is again philosophical. It does not rest on any direct evidence. The argument has been the subject of substantial debate. The debate is not settled. I mention it not because it is necessarily right. I mention it because it is one of the candidate explanations that has been seriously discussed in the literature. The literature, when it considers the Fermi Paradox, considers a very wide range of possibilities. The simulation hypothesis is one of the more exotic. There are others. The full taxonomy is large. What we have when we sit with all of this is a question with many possible answers, none of which has been definitively established. The question is alive. The answers are tentative. We continue to look. Let me also walk through what is sometimes called the rare Earth hypothesis, because it is one of the more specific versions of the simpler explanations. The rare Earth hypothesis, articulated in detail by Peter Ward and Donald Brownlee in their book of that name, in 2000, holds that the conditions necessary for complex life are far rarer than the conditions for simple life. The reasoning involves specific features of our planet. We have a stable orbit. We have a single large moon that stabilizes our axial tilt. We have a magnetic field that protects us from solar wind. We have plate tectonics that recycles carbon. We have a stable star that has not, in our history, suffered violent flares. We have a position in the galaxy that is far from supernovae and other catastrophic events. Each of these conditions, the authors argue, is independently rare. The intersection of all of them in a single world is correspondingly very rare. Most habitable planets in the rare Earth picture do not have the full set of conditions necessary for complex life. They may have simple life. They may have microbial ecosystems, but they do not have the chain of events that, on Earth, produced multicellular life, intelligence, and technology. Let me walk through each of the conditions briefly, because each is, in some sense, a separate question. The stability of our orbit is set by the configuration of the giant planets in our solar system. Jupiter, in particular, has acted as a kind of gravitational shepherd, deflecting incoming comets and asteroids that might otherwise have struck Earth. Without Jupiter, in roughly its current configuration, our orbit might still be stable, but our impact history would have been very different. Whether such a configuration is common in other star systems is, on current evidence, a question of statistics. The answer is being constrained slowly as exoplanet surveys grow. The single large moon that we have is, in cosmic terms, unusual. The moon is roughly 1/4 the diameter of the Earth. Most rocky planets do not have such a large companion. The moon contributes to our axial stability. Without the moon, our axial tilt might wobble over geological time, producing climate variations that could destabilize complex ecosystems. The magnetic field that protects us from solar wind is sustained by the molten iron core of the Earth. The core remains molten because of residual heat from the planet's formation and from radioactive decay. The exact conditions for sustaining a long-lived magnetic field are, on current understanding, somewhat specific. Mars, for instance, lost its magnetic field early. Without the field, much of its atmosphere was stripped by the solar wind. Earth's continued magnetic protection is, in this sense, a contingency. Plate tectonics, similarly, is a feature of our particular planetary chemistry and dynamics. Plate tectonics drives the carbon cycle that has, over geological time, regulated our climate. Without plate tectonics, the carbon dioxide in our atmosphere would have either accumulated to runaway greenhouse levels, as on Venus, or been depleted to glacial levels, as on Mars. Plate tectonics keeps us in the middle. The stability of our star is, by stellar standards, relatively unusual. Many stars produce violent flares that would, periodically, strip the atmospheres of nearby planets. Our Sun has been comparatively quiet over the timescales we have observed. The reasons are partially understood, but the long-term variability of Sun-like stars is an active research area. The position of our solar system in the galaxy is also in some sense favourable. We are far from the galactic centre, where high stellar density would produce frequent close encounters and supernova exposures. We are in a sparse region of the disk where the cosmic radiation is relatively low and the encounter rate with other stars is small. Whether such positions are common is a question of galactic statistics. Most stars are in denser regions than ours. The intersection of all of these favorable conditions is, the rare Earth argument says, rare. Each condition by itself may be modestly probable. The intersection of all of them, in a single planet at a single moment, is much less probable. Multiplying through the conditional probabilities, the rare Earth argument concludes that complex life, of the kind that produces technology, may be very rare indeed. This is again a candidate explanation. It is consistent with the data. It is not by itself conclusive. The rare Earth hypothesis is, in some sense, a specification of the early filter argument. It identifies particular steps that may be the bottlenecks. It is consistent with the data. It implies that we may be exceptional, not because the universe is hostile, but because the chain of contingencies required for our existence is long and improbable. The hypothesis has its critics. Some of the conditions identified by Ward and Brownlee are, in light of subsequent research, not as rare as they argued. Exoplanet surveys have found many systems with conditions roughly comparable to ours. The full set may still be rare, the individual conditions may not be. The hypothesis sits today as one of the candidate explanations. It is plausible. It is not established. What we have again is the silence. The silence is consistent with the rare Earth picture. It is also consistent with several other pictures. Now let me bring this closer, fellow night watcher. I want to consider for a moment what we should actually do about all of this, not as a matter of practical policy, but as a matter of how we ought to hold the question. If the dark forest is real, then we have, by past broadcasting, made an error that we cannot correct. The signals have left. The consequences, if any, are in transit. If the great filter is ahead of us, then we have, in some sense, a finite time to figure out what the filter is and how to avoid it. If we are simply alone in our galaxy, then we have a long path ahead of us, but no immediate threats. We can take our time. If civilizations exist but use undetectable methods, then we may, in time, learn to detect what they are saying. If the zoo hypothesis is correct, then we may, in time, prove ourselves worthy of contact and be welcomed. Each of these scenarios implies a different response. We do not know which is correct, so we cannot, with certainty, decide on the right response. What we can do is continue to look. The search has been ongoing for 70 years. The instruments are improving. The fraction of the search space we have covered is growing. In time we may find a signal, or we may definitively rule out signals at certain levels. Either result will be informative. We can also continue to learn about ourselves. The filter, if it is real, and if it is ahead of us, may be something we can recognize and avoid. The avoidance may not be easy, but it may be possible. These are the actions we have available. They are modest actions on the scale of the question, but they are the actions we can take. Let me hold the modesty of those actions for a moment. We are listening, with our small terrestrial instruments, to a galaxy that contains hundreds of billions of stars. Our coverage of the search space is, as I mentioned, on the order of 1 part in a quintillion. We have, in some sense, only just begun. The work is patient. The work is slow. The work proceeds across generations of researchers, each adding their measurements to the cumulative record. The record grows, the understanding refines. What we have at any given moment is a snapshot of the cumulative listening. The snapshot today says that, in the small fraction of the search space we have covered, we have heard nothing that has been confirmed. Tomorrow's snapshot may say something different, or it may say the same thing, or it may say something we have not yet imagined. We do not know what tomorrow's snapshot will say. We only know that the listening continues. The Vera Rubin Observatory in Chile, beginning full operations in 2026, will image the southern sky every 3 nights at depths beyond any previous survey. The survey is primarily designed for other purposes, but it will, in passing, identify many candidate technosignatures that can be investigated by other instruments. The James Webb Space Telescope is, as of this recording, conducting infrared spectroscopy of distant exoplanets. The spectra contain information about atmospheric composition. Some of that information, in principle, could include the signatures of industrial activity. Markers like chlorofluorocarbons, which have no known natural source, would be unambiguous evidence of an artificial process. So far, no such signature has been detected. The search continues. The square-kilometre array, planned for the next decade, will provide unprecedented sensitivity in the radio band. It will, by current estimates, expand our coverage of the search space by orders of magnitude. Each of these instruments will add to the cumulative record. Each will refine our understanding of what the silence means. We will not know for some time whether the silence is genuine or whether it is an artifact of insufficient instrumentation. The two possibilities, at present, are observationally indistinguishable. They will, with time and more careful work, become distinguishable. The work continues. Let me also walk through one more candidate that I think is worth holding. The candidate is sometimes called the youngness hypothesis. The idea is this: suppose that the conditions for technological civilization in the long history of the universe have only recently become possible. The early universe was hot, dense, and chemically simple. The first generations of stars produced the heavy elements that are necessary for rocky planets and complex chemistry. But it took several generations of stars to enrich the interstellar medium enough to make Earth-like planets common. Some calculations suggest that the heavy element abundance required for terrestrial-style planets only reached current levels in the last few billion years. Before that, the chemistry was insufficient. The planets did not have enough silicon, iron, oxygen, carbon, in the right concentrations to produce the kinds of bodies we are familiar with. In this picture, the galaxy may in fact be in its early phase of producing technological civilizations. We may be early. The galaxy may, in the next billion years, produce many more civilizations. The galaxy may, in the next 10 billion years, become richly populated with intelligence. But at this particular moment, in the slice of cosmic time we happen to inhabit, the population may simply be small. Not because of any filter, not because of any concealment, but simply because the conditions have not been right for long enough. This is, again, a comforting reading. It says that we are early. It says that intelligence is, in some sense, just getting started in our galaxy. It says that our solitary listening is not pathological, but simply consistent with where we are in cosmic history. The picture has its critics. The chemistry argument is contested. The youngness of intelligence does not, by itself, explain why no civilizations have arisen, even in the last few billion years, when conditions have been adequate. The picture is one candidate among many, but it is, in the spectrum of possible explanations, one of the more hopeful. It says that the silence may be a transient feature of our cosmic moment, and that the galaxy may, in the long run, become much more populous. We will not, of course, live to see that. The relevant timescales are on the order of billions of years. By the time the galaxy fills up, in this picture, we and all our descendants will be long gone. But it is perhaps a comforting thought to hold. The silence may not be the silence of an empty galaxy. It may be the silence of a galaxy that is, in some sense, still being born. Now let me come back to the speck of light in the sky. Every star we see, in any direction we look, is a candidate. Every star may host planets. Every habitable planet may host life. Every life-bearing planet may produce intelligence. Every intelligent species may, at some moment in its history, build instruments capable of detecting other intelligences. So far as we can tell, we are the only such species in our reach. Let me hold what our reach means for a moment. Our reach, defined by our current instruments and our current understanding, is roughly the part of the galaxy we can survey for technological signatures. Within that part, perhaps a few thousand light years in radius, we have done our most careful work. Beyond that, our coverage is sparse. Beyond the galaxy itself, our coverage is essentially nil. Within our reach, we have found nothing confirmed. Beyond our reach, the universe could contain anything. Other civilizations may exist. Other civilizations may have arisen and ended. Other civilizations may, even now, be looking back at our small star and wondering about us. We do not know. The reach defines the boundary of our knowledge, not the boundary of what exists. In time, the reach will extend. New telescopes will be built. New surveys will be conducted. The fraction of the galaxy we have inspected, with care, will grow. The growth is slow. The growth is patient. The growth proceeds across human generations. This may be because we are unusual. It may be because the others are silent. It may be because the others have not survived. It may be because the others use channels we cannot read. It may be because the galaxy is so large that none of us are in detectable range of each other. We do not know. What we have when we look up at the night sky is the same sky that Fermi looked at in his Los Alamos cafeteria in the summer of 1950. The same questions. The same silence, the same lack of resolution. 70 years have passed. We have built telescopes, we have run surveys, we have refined our theories. We have asked the question more carefully, more precisely, more rigorously. We have not, in any decisive way, answered it. The silence persists. Now let us hold this. The silence, whatever its cause, is the most important data we have about our place in the cosmos. The silence shapes our expectations. The silence informs our policies. The silence carries, in its absence of content, an enormous amount of information. We do not know what the information says. We continue to listen. The work continues. Let me also walk through a few of the more practical implications of all of this for our own civilization. If the dark forest argument is correct, then our broadcasting has been a strategic error. We have, since the early 20th century, been emitting radio and television signals that have travelled outward at the speed of light. The signals have, by now, reached every star within a radius of approximately 100 light-years from Earth. Within that sphere, there are roughly 15,000 stars, of which perhaps a few thousand host planets in temperate zones. If any of those star systems contains a civilization that has detected our signals, our location is, in principle, known to them. Whether they will act on that knowledge depends on their motivations, their capabilities, and their values. We do not know any of these. The signals continue to travel. With each passing decade, the sphere of our broadcasting grows. By the end of the next century, the sphere will include hundreds of thousands of stars. By the end of the next millennium, the sphere will include nearly the entire galactic neighbourhood. There is, as I mentioned, nothing we can do to retrack the signals. They have left. They are in transit. They will continue to travel. What we can do, going forward, is decide whether to continue broadcasting deliberately. The SETI community has, by consensus, moved away from deliberate, active broadcasting. Programs like the original Arecibo message of 1974, which sent a coded transmission toward the globular cluster M13, are not being repeated. The community has, in effect, adopted a precautionary principle. The principle says that, in the absence of certainty about the consequences of broadcasting, we should refrain. Whether this caution is correct is, as I have said, an open question. The dark forest argument may be wrong. The risks may be overstated. The benefits of communication may, in some configurations, exceed the risks. But the caution is, at present, the consensus position. The community has decided to listen, not to transmit. This decision has, by itself, no enforcement mechanism. Individual nations, individual organizations, or individual researchers might choose to broadcast independently. There is no global treaty on the matter. There is no enforcement body. The decision is, in essence, a soft cultural consensus. Whether the consensus will hold indefinitely is unclear. Various proposals for active broadcasting have been advanced in recent decades. None has been carried out at scale, but the proposals continue to appear. If even one civilization-wide decision to broadcast were made, the dark forest argument, if correct, would apply. For now, we mostly listen. Stay with me here for a moment while we consider the question one more time. If the galaxy is empty, then we are responsible for what intelligence does in this region of the universe. The galaxy is ours to inherit or to lose. The choice, in some sense, is ours. If the galaxy is silent because of fear, then we are in a galaxy of hidden watchers. The silence is a strategy. The strategy may not save us, but it may at minimum reduce the chance of attracting attention. If the galaxy is silent because of failure, then we are in a galaxy of ruins. The filter, whatever it is, has done its work many times. We do not know if it lies behind us or ahead of us. Each of these possibilities is, in its own way, sobering. Each is, in its own way, instructive. Let me hold the ruin scenario for a moment, because it is one of the more vivid candidate explanations. Imagine that the galaxy is, in fact, full of civilizations that have at some point arisen, developed technology, expanded, and then collapsed. The collapses in this picture may take various forms. Some civilizations may destroy themselves through their own actions. Others may be destroyed by external events. Others may simply run out of resources and decline. If this picture is correct, the galaxy is, in some sense, an archaeology field, rather than a field of contemporary observers. The remains of past civilizations would, in principle, be detectable. We might see, in the right places, evidence of large-scale engineering that has been abandoned. Dyson spheres, partially built. Industrial atmospheres slowly returning to natural chemistry. Stars that have been moved into unusual configurations. The search for such remains is ongoing. The techno-signature programs I mentioned earlier include searches for these kinds of ruins. So far, no clear example has been identified. This may mean that the picture is wrong. The ruins, if they existed, might not be detectable at the distances we can probe. The ruins might have decayed beyond recognition. The ruins might never have been distinctive enough to stand out from natural processes. Or this may mean that the picture is right, but the ruins are not where we have looked. The galaxy is large. The places we have searched are few. We do not know. What we know is that we have not, so far, found evidence of large-scale ruined civilizations in the patches of sky we have inspected with care. That fact, like the absence of confirmed signals, is consistent with multiple interpretations. The picture is, again, ambiguous. What we have as observers, as listeners, as writers of small careful notes in our small careful notebooks, is the sky. The sky has been here for 13.8 billion years. The sky has been silent, to our best ability to listen, for the 70 years that we have been able to listen at all. The silence is what we have. We are walking through it, slowly, tonight. Let me hold something more. The Fermi Paradox is, in some sense, a problem of timing. The galaxy is old. The galaxy has had time to produce many civilizations. The galaxy has had time to receive signals from many directions. But timing matters. A civilization that arose 1 billion years ago and lasted only a few thousand years would have left no detectable signal by now. The signal would have travelled into space, expanded, dispersed, dimmed beyond detection. We would not, even with our best instruments, see it. A civilization that arose only a few hundred years ago and is still active would have left signals that have travelled only a few hundred light years. Most of the galaxy is outside that radius. We would not, in most directions, see it. The window of detectability for any given civilization is narrow. The civilization must be close, it must be still active. It must be using channels we can read. The intersection of these conditions for any random civilization in the galaxy is small. This is, in some sense, a softer version of the filter argument. It does not require destruction. It only requires that the windows of detectability rarely overlap. The galaxy may be in this picture, full of intelligence. The intelligences may mostly exist outside one another's detection windows. The result is the same silence we observe. This is perhaps the gentlest version of the explanation. It implies neither destruction nor concealment. It implies only the natural difficulty of catching another civilization in its window. Let me also walk through one more candidate that has gained attention in recent years. The candidate is sometimes called the convergent ascension hypothesis. It is, in some sense, related to the indifference variant of the silent civilizations argument. The idea is this: suppose that any sufficiently advanced civilization, given enough time, develops in ways that we cannot easily anticipate. The civilization may perhaps leave its physical substrate and exist in some other form, perhaps as patterns of information running on computational structures we cannot detect. The civilization may perhaps retreat into virtual environments of its own construction, abandoning the physical universe as uninteresting. The civilization may perhaps evolve into something so different from our concept of civilization that we would not recognize it as such, even if we encountered it. The convergent ascension picture suggests that the developmental trajectory of intelligence may, over millions of years, lead away from the kinds of activities that produce detectable signals. Old civilizations do not broadcast because they have moved beyond the use of broadcasting. They do not build large physical structures because they have moved beyond the use of physical structures. They do not occupy planets because they have moved beyond the need for planets. In this picture, the galaxy may be full of post-physical civilizations that are, in some sense, around us all the time, but that we cannot detect with our current instruments because their existence is not on the scales we can measure. This is, I want to emphasize, speculative. It is not directly testable. It rests on assumptions about the long-term trajectory of intelligence that we cannot, at present, verify, but it is, in some sense, internally consistent. It explains the silence, it accommodates the data. It is one of the more curious candidate explanations in the literature. The literature, as I have noted, contains many such candidates. The full taxonomy is large. The question is, in some sense, an invitation to think about all the ways that the silence might be explained, and to weigh each one against the data we have. The data in the end is the silence itself. The silence supports many different stories. The silence resolves none of them. We continue to listen. We may in time catch one. The Vera Rubin Observatory, beginning operations in 2026, will deepen our sky surveys. The Breakthrough Listen program will continue. New surveys will come online. The cumulative coverage of the search space will grow. If even one signal is caught, the entire picture changes. The galaxy goes from silent to populated. The filter argument changes shape. The dark forest hypothesis becomes harder to maintain. The other explanations rise or fall accordingly. So far, no signal has been caught. So far, the silence persists. Let me hold the implications of what catching a single signal would do for our cosmology. If we caught a single, confirmed signal of artificial origin, the consequences would propagate through every level of our thinking about the universe. First, the basic question of whether life is rare would be settled. At least one other species somewhere in our galactic neighborhood would have produced technological civilization. Life, intelligence, and technology would all be confirmed as repeatable phenomena in our cosmos. The Drake equation would be partially anchored, with at least one term established. Second, the question of the Great Filter would be partially resolved. If the signal comes from a civilization that has clearly passed beyond our current level of development, then the late candidates for the filter become less likely. We would have evidence that civilizations can, in fact, survive past whatever the filter step turns out to be. This would shift our expectations about our own future in a substantially more hopeful direction. Third, the dark forest hypothesis would face severe pressure. If a civilization were willing to broadcast, then the strategic equilibrium that the dark forest argument predicts cannot hold for all civilizations. Some other equilibrium would be operating. Perhaps the broadcasters are very old and feel secure. Perhaps the broadcasters do not believe there are predators. Perhaps the broadcasters have, by some means, neutralized the threat of predators. Whatever the explanation, the simple dark forest argument would need to be refined or replaced. Fourth, the question of what to do next would become urgent. A confirmed signal would prompt a global discussion about whether to respond. The discussion would involve deep policy questions. The discussion would involve, almost certainly, a careful weighing of the dark forest considerations against the value of communication. The outcome of the discussion is not, at present, predictable. These are some of the consequences of catching a single signal. They are large. They are transformative. Catching a signal has not yet happened. Catching a signal may never happen. The probability of catching a signal, given our current instruments and search strategies, is not well known. Some estimates put it at meaningful levels, perhaps a few percent per decade of continued listening. Other estimates put it at vanishingly small levels, given the size of the search space. The estimates depend on assumptions that cannot at present be verified. The estimates will be refined as more data comes in. For now, we listen. The probability is, by all estimates, small, but it is not zero. And in cosmology, as in many other deep questions, the rare events are the ones that change everything. So we wait, so we listen, so we record. And sometimes we ask the question that Fermi asked at lunch in 1950. Where is everybody? Let me hold one more thread before we close. There is a question about the timing of our own listening that I want to be honest about. We've been listening for 70 years. In the cosmic timescale of the galaxy, 70 years is essentially nothing. The galaxy is roughly 13.5 billion years old. Our listening represents less than one part in 200 million of the galaxy's history. It is, by any metric, a vanishingly small fraction. What this means is that, even if civilizations occasionally broadcast, the probability that any one of those broadcasts is currently in transit through our particular small patch of space, at the particular wavelengths we are listening on, with the particular geometry we can detect, is small. The broadcasts may have happened in the past. They may happen in the future. They may not be passing through us right now. This is, in some sense, the most likely explanation for the silence we have heard so far. We are not necessarily in a galaxy without broadcasters. We may simply be in a galaxy where the broadcaster's signals are not at present passing through our location. If we listen for another 70 years, the situation may be the same, or it may be different. We do not know. The honest position, in the face of all of this, is that the silence is, at present, ambiguous. The silence does not by itself tell us that the galaxy is empty. The silence tells us only that the galaxy, in the small fraction we have been able to listen to, has not produced a confirmed signal yet. Whether that pattern will continue, or whether it will eventually change, is something we cannot know without more data. We continue. Now let me sit briefly with a question that comes up in the literature, which is how we should think about our own existence in light of all of this. We are, by all evidence, a young civilization. Our species has existed for roughly 200,000 years in its current form. Our technological civilization has existed for roughly 10,000 years. Our radio capability is 70 years old. We have, in some sense, just opened our eyes. What we see, in our newly opened eyes, is a silent universe. The silent universe may or may not be silent because it is empty. The silent universe may or may not be silent because of any of the explanations we have walked through tonight. The silent universe is silent. That is what we have. Our position as a newly opened pair of eyes is fragile. We do not yet know if we will survive past whatever the relevant filter turns out to be. We do not yet know if we have already broadcast our location to a galaxy of careful hunters. We do not yet know if we are alone, hidden among the hidden, or simply too far from anyone for contact to matter. What we do know is that we have, in the brief moment since we opened our eyes, become aware of the question. We have asked it. We have thought about it. We have searched, in our limited way, for answers. The asking is, in some sense, the human contribution. The asking is what we add to the universe. The universe runs its course, with or without us. We add the question. The question is whether anything else, in the long history of the cosmos, has added a question of its own. We do not know. We listen. Now let us come, slowly, to a quiet close. Tonight we have walked through what the Fermi Paradox is. We have walked through what the silence means, or what it might mean. We have walked through 3 classes of explanation, and within those, several subclasses. We have walked through the dark forest hypothesis, which is the version nobody wants to be true, the version that says that civilizations exist but hide, that the cost of being detected is annihilation, that we have already made an error by broadcasting. We have walked through the great filter, which is the version that asks whether the difficult step is behind us or ahead. If behind, we are lucky. If ahead, we are not. We have walked through the simpler versions, which say that life is rare, or that civilizations are rare, or that the timing rarely works out. We have walked through the exotic versions, which say that communication uses channels we cannot read, or that the galaxy has decided to leave us alone. We do not, at the end of all of this, know which version is correct. What we have is the silence. The silence is, in itself, ambiguous. It is the most important fact we have about our place in the cosmos. It tells us, depending on how we read it, that we are alone, or hidden among the hidden, or one of the few to have made it past the filter, or one of many about to face it. The silence does not resolve. We continue to listen. If you have come here to rest, let this carry you. The silence is what the night gives us. It has been here, in some form, for as long as there has been a night. The silence is not, by itself, dangerous. It is only, perhaps, vast. The vastness, when we sit with it, is what makes the question hard. We are small. The cosmos is large. The cosmos has been here for a very long time. The cosmos may be full of others, or empty, or somewhere in between. We do not know. What we have is our own listening. We have our instruments, our surveys, our patient programs of observation. We have our questions. We have, in some sense, our seat by the open window of a very long night. We sit, we listen, we record what comes through. So far, no signal. So far, the silence. Now let us pull back. One more time. The Fermi paradox is, in its essence, a paradox of expectations against observations. The expectations were that the galaxy should be loud. The observations are that the galaxy is quiet. The mismatch is the puzzle. The puzzle has, over the 70 years it has been formally articulated, resisted resolution. Each new survey, each new instrument, each new theoretical framework has refined the question without answering it. This is, in some sense, the texture of deep cosmological questions. They are not resolved quickly. They are resolved, if they are resolved at all, over the course of generations of careful work. The work continues. What we have at this moment, in this hour, in the room where you are listening, is the same silence that Fermi heard at his lunch table in 1950, the same silence that has accompanied human listening for the 70 years since, the same silence that may or may not, in some future moment that none of us will live to see, be broken by a signal that arrives from somewhere we did not expect. The signal, if it comes, will change everything. The signal has not yet come. The silence is what we have. Let me hold one more thing, and then I will let you rest. The dark forest hypothesis, the version nobody wants to be true, is, in the end, a guess. A reasonable guess informed by game theory and by the constraints of physics, but a guess nonetheless. It is not a confirmed observation. It is not an established theory. It is a frame for thinking about what the silence might mean. The frame is, in many ways, the darkest available. It is also in many ways the most consistent with the data we have. If the galaxy were full of careful, silent civilizations, the sky would look exactly the way it does. Empty. This is the version that nobody wants to be true. This is the version that, when we sit with it carefully, we cannot rule out. It may be wrong. It probably is, in some of its details. The full picture, whatever it turns out to be, is probably more complex and more nuanced than the simple version of the hypothesis suggests. Let me also walk through one final wrinkle. Suppose that the dark forest argument is partially correct, but that the consequence is not annihilation in any dramatic sense. Suppose that the consequence is, instead, what we might call epistemic isolation. In this picture, Emil Konopinski, the equilibrium pressure that emerges in the galaxy is not that civilizations destroy each other, but that they avoid each other. They do not establish contact. They do not communicate. They do not interact. They live their separate cosmic lives in mutual ignorance. This picture is, in some ways, less terrifying than the strong dark forest argument. It does not require that any civilization is being destroyed. It only requires that civilizations have, over the course of cosmic experience, learned that contact does not work. The contact attempts fail. The contact attempts produce misunderstandings. The contact attempts produce, in the worst cases, conflict. So over time, the civilizations stop trying. The galaxy in this picture is populated but disconnected. Each civilization, in its own corner, does its own work. None of them broadcasts to the others. None of them attempts contact. The picture is still consistent with the silence we observe, but it is a softer picture than the version where the consequences of broadcasting are existential. We do not know which version, if either, is correct. What we have again is the silence, but the simple version, as a hypothesis, sits there, in the literature, unrefuted. It is one of the candidate answers to a question that has not yet been answered. We do not know if it is correct. We may never know. What we have is the silence. Tonight we have walked through what the silence might mean. We have walked through the dark forest. We have walked through the great filter. We have walked through the simpler answers and the more exotic ones. We have, in a careful and patient way, considered the question from several angles. Let me hold one more thread before we close. The Fermi Paradox, as we have walked through it, is fundamentally a question about probabilities. The probability that life arises, the probability that intelligence emerges, the probability that civilizations broadcast, the probability that civilizations survive. Each of these probabilities is, at present, very poorly constrained. Our best estimates, even from researchers who have spent decades working on the question, span many orders of magnitude. This uncertainty is, in some ways, the deepest fact about the question. We do not know. We do not know how to estimate. The estimates we make are educated guesses, derived from arguments and analogies, but they are not, in any rigorous sense, measurements. What this means, practically, is that almost any answer to the Fermi paradox is consistent with the data, given appropriate adjustments to the priors. The dark forest can fit. The great filter can fit. The rare earth can fit. The simulation hypothesis can fit. The simple absence of civilizations can fit. Each of these is, in some configuration of the priors, consistent with the silence. The science of the question is, in part, the science of constraining the priors. As we collect more data, the range of consistent priors should narrow. As the range narrows, the question should become more answerable. The data collection is ongoing. The constraint is slowly being applied. The answer, if it comes, will come slowly. Now let me sit with what this means for the way we should approach the question. The question is, in many ways, an exercise in epistemic humility. We do not know. We cannot at present know. The honest position is to acknowledge the uncertainty, to lay out the candid explanations, and to continue the work of constraining the priors with more observation. This is not a satisfying position. Most questions, in most domains of human inquiry, eventually yield to investigation. The Fermi Paradox has not, in 70 years, yielded. It may not yield for another 70 years. It may not yield for several centuries. In the meantime, we hold the question. We do not force an answer. We do not pretend to certainty. We continue the work. This is, in some sense, what science is for. Not to give answers quickly, not to give answers definitively, but to set up the conditions under which, with enough patience and enough effort, answers may eventually emerge. The Fermi Paradox is one such question. The work continues. Let me also hold this. The question has, in the 70 years since Fermi posed it, become a part of our culture. It has appeared in novels, in films, in popular essays, in academic textbooks. The general public has, in some form, encountered it. The question is, in this sense, more than a scientific puzzle. It is a cultural touchstone. It is one of the things we, as a species, think about when we think about our place in the universe. And this cultural presence is, in itself, interesting. The question has become, in some sense, part of what it means to be human in the present era. The previous era, before Fermi's lunch in 1950, did not have this question. The question is, in some sense, a recent acquisition. It joins in our cultural baggage other questions of similar weight. What is consciousness? What is free will? What is moral obligation? What is the nature of reality? The Fermi Paradox is, in this sense, a cosmic question that has become a human one. It is, in some sense, the universe asking us about ourselves. We are still working on the answer. Hold this. The cultural presence of the question is, in itself, a kind of evidence about us. It is worth holding what it means that 60 years after the formal scientific question was posed, the question has spread throughout our culture. The question appears in films and novels. The question appears in discussions of policy and philosophy. The question appears in popular journalism. The question, in some sense, has become a feature of how educated people think about their place in the universe. This spread is, in itself, unusual. Most scientific questions remain confined to their academic communities. The Fermi Paradox is one of the few that has crossed into the general culture. It has done so because the question is, at its core, asking something most people, given enough time to think about it, will find themselves asking. Are we alone? Are there others? What are they like? What does our silence mean? These questions are, in some sense, universal. They predate the formal version of the paradox. They appear in mythology, in religion, in early speculation about the heavens. What is new is the formal framework, the systematic investigation, the careful weighing of evidence. The formal framework will continue to develop. The investigation will continue. The weighing will continue. The question, in its formal version, will eventually find better answers than we have today. The question, in its general version, will perhaps always be with us. We have, as a species, become aware enough of our cosmic context to ask the question. We have built the instruments, we have developed the theoretical frameworks, we have published the papers. We have, in some sense, demonstrated that we are capable of being curious about our cosmic neighbours, whether or not they exist. That capability is, in some sense, what the dark forest argument fears. The argument assumes that other civilizations are capable of the same curiosity, the same instrumentation, the same investigation. The argument assumes that they may also have the means to act on what they discover. If we are, in this sense, a typical young civilization, then we are doing what young civilizations do. We are looking. We are asking. We are revealing our location to anyone who can hear us, whether or not we mean to. This is, in some sense, the human position. We are early. We are loud. We are not careful. We have not yet developed the institutional structures that would, in the dark forest picture, push us towards silence. If the picture is correct, our continuing loudness is a strategic vulnerability. If the picture is wrong, our loudness is, perhaps, a courageous announcement that we are here. Which it is, we do not know. Now let me hold the quiet end of this for a moment. We live, all of us, on a single planet. The planet rotates beneath our feet. every 24 hours, carrying us through the day-night cycle of Earth. The planet orbits its star every 365 days, carrying us through the seasons. The star, in turn, orbits the center of our galaxy every 225 million years, carrying us through the broader galactic year. Within this nested set of orbits, we live our small lives. We have our concerns, we have our work, we have our quiet evenings and our quiet nights. The cosmos goes on. The galaxy spins. The stars age. The expansion continues. The silence persists. Let me hold this image for a moment. The galaxy, as it has been for many billions of years, is a slowly turning disk of stars and gas, embedded in a larger halo of dark matter, drifting through the broader cosmic web. The disk has its arms. The arms have their stars. The stars have their planets. The planets have, in some cases, their oceans, their atmospheres, their geological and biological systems. We are on one such planet. We are in one such star system. We are in one such arm of one such galaxy in one such region of the cosmic web. Around us, the same kinds of structures repeat. Other planets, other star systems, other arms, other galaxies. The repetition is, by current cosmological understanding, vast. The observable universe contains hundreds of billions of galaxies. The full universe, beyond what we can observe, may be much larger still. In all of this vast repetition, we have not yet, with certainty, detected another civilization. This may be because we are special. It may be because we are early. It may be because the others are hiding. It may be because the others have not survived. It may be because we have not yet looked far enough or carefully enough. The data by itself does not tell us which. The cosmos goes on. The galaxy spins. The stars age. The expansion continues. The silence persists. This is the texture of where we are. We are very small. The cosmos is very large. The questions we ask when we look at the sky are not, in any simple sense, our questions. They are the questions that the cosmos has set for us. The cosmos, of course, does not know we are asking. The cosmos does not have intent. The cosmos is simply what it is. We are the ones who have, in our small recent moment, learned to point at the sky and ask. What we ask of ourselves. The asking is, in the end, our own. The silence is not, in this sense, an answer to anything we have asked. The silence is simply what is there. We are reading it, in the way we read all the other features of the cosmos, by inference from the data we collect. The data so far is consistent with many readings. We have not yet settled on one. We continue. Let me also, in closing, hold the way that this question connects to the broader human enterprise of understanding our place. For most of our species' history, we did not know that the Earth was a planet. We did not know that the sun was a star. We did not know that the stars were other suns. The understanding of our cosmic context is a recent development, accumulated over the last several centuries of careful work. In the same span of time, we have learned a great deal about the universe. We have learned about its age, its size, its general structure. We have learned about the laws of physics that govern its behavior. We have learned about the chemistry, the geology, the biology of our own world. We have also, in the same span of time, learnt that we may not be alone, or that we may be alone in a particular way. We have not yet resolved which. The Fermi Paradox, in its modern form, is the boundary of what we know and do not know about our cosmic neighbours. The boundary is, in some sense, the leading edge of our investigation. It is where the next generation of work will take place. The boundary will, with more data, move. The unknown will become smaller. The known will grow. This is what science does. It moves boundaries. It does not always answer the deepest questions. It does, slowly, refine the way the questions are asked. The Fermi Paradox is one of the deepest questions. It has been refined over the 70 years it has been studied, but it has not been answered. The work continues. In closing, let me return to the night sky. If you look up on any clear evening, you can see a few hundred stars without any optical aid. Each star is, in some sense, a small reminder of the question. Each star is a potential host. Each star, by present statistics, is more likely than not to have planets. Some of those planets may be habitable. Some of those habitable planets may host life. Some of that life may, at some moment in its long history, have asked the question that Fermi asked at lunch in 1950. Where is everybody? The asking is, in some sense, universal. Any sufficiently curious species, given enough time and the appropriate instruments, would arrive at the question. We have arrived at it. Whether anyone else has arrived at it, we do not know. The sky is silent. The silence is the data. The data does not by itself distinguish among the candidate answers. We continue to listen. We have not, at the end of all of this, arrived at an answer. What we have arrived at is the question itself, more clearly seen. The question is what the silence means. The question is what our place in the cosmos is. The question is whether we are alone, or hidden, or doomed, or simply early. The question has been with us in some form for 70 years. The question will be with us in some form for a long time more. We continue to ask, we continue to listen. The night is long, the sky is wide. The answers, if they come, will come slowly. That is the texture of what we are doing here tonight. Let me also walk through what I think is the most honest summary of the position we are in. We are a young species. Our scientific civilization is only a few centuries old. Our serious cosmology is only a century old. Our serious search for extraterrestrial intelligence is only 70 years old. By cosmic timescales, we have only just begun. Given that we have only just begun, the silence we have so far observed is, in some sense, premature. We have not yet looked at most of the possible places, most of the possible frequencies, most of the possible times. The fraction we have looked at is, as I have said, very small. The remaining fraction is enormous. So when we say that we have heard nothing, we are saying that we have heard nothing in the tiny corner of the search space we have so far inspected. The rest of the space is, by current technology, unexplored. The honest reading of the silence, then, is not that the galaxy is empty. The honest reading is that we have not yet, with the instruments and the time we have had, found anything. The two readings are different. The first is a conclusion. The second is a status report. The status report at present is that the search continues. The search is incomplete. The result is at present null. The null result, given the small fraction of the search space we have covered, is consistent with many different actual states of the galaxy. We do not yet know what the galaxy contains. We have not yet finished looking. This is the position. This is the honest description of where we are. Hold this. The silence we are listening to has been here for as long as there has been a sky. It will be here, in some form, for as long as we continue to listen. It is, in a real sense, the dominant acoustic feature of the cosmos. The cosmos, as far as we can tell, is mostly quiet. We sit in our quiet planet, in our quiet star system, in our quiet arm of an ordinary galaxy. We listen. We record. We wonder. The wondering is perhaps the most human part of all of this. We are the species that asks. We are the species that records. We are the species that, given a silence, tries to understand what the silence means. The silence may not mean anything. The silence may mean everything. We do not know. We continue. Let me hold the wondering for one more moment. The wondering, as a feature of consciousness, is not, as far as we know, common in the universe. Most of the universe does not wonder. Most of matter, most of energy, most of the structures of cosmology simply do what they do without asking why. We as a species are different. We wonder. We notice that we are noticing. We ask what it means. We try in our small way to fit the noticing into a larger picture. The Fermi Paradox is, in some sense, the wondering applied to the question of whether we are alone in the wondering. We ask whether anyone else, anywhere in the galaxy, is doing what we are doing. We ask whether anyone else has built telescopes, run surveys, written papers, debated theories. So far as we can tell, no. This may be because we are the only ones. It may be because the others are silent. It may be because the others have not yet developed the capacity. It may be because the others have already lost the capacity. We do not know. The wondering in its way is one of the most distinctive things about us. We share many features with other species on Earth. We share in some sense our basic biology with most of the natural world. But the wondering, in its full reflective form, is a feature that, as far as we have been able to detect, is unique to us. Whether it is unique only on Earth, or unique in the broader cosmos, is precisely the question we cannot yet answer. We continue. Hold this last image. Somewhere in the night sky tonight there is a star whose light has been travelling for hundreds of years to reach us. Around that star perhaps there is a planet. On that planet perhaps there is something living. The light from that something, if it broadcasts, is still in transit. The light may, in some future moment, arrive at our telescopes. We may, in some future moment, recognize what we are hearing, or we may not. Either way, the work of listening continues. The work is patient. The work is slow. Thank you for staying with me through this story.